This is part 2 of the video that introduces nodal analysis. And as you can see from the diagram, we're already well into the example. So if you haven't looked at part 1, you probably ought to, because this may not make a lot of sense unless you've looked at part 1. So in part 1, we found an equation applying Kirchhoff's current law at nodes 1 and 2. Now we're at the point where we need to find an equation at node 3, again applying Kirchhoff's current law. So to do that, first I'll tidy up a bit of space. And I'm beginning to think that this particular layout represents poor planning on my part, which you probably have noticed only occurs very infrequently. Okay, so what I need now is to apply KCL at node 3. Okay, so I will look at this and say I've got 4 milliamps coming in from my source, and then I'll define a current IA leaving node 3 to the left, and IB leaving node 3 down. And we can say then that IA plus IB is equal to 4 milliamps. Okay, well, IA is going to be the current through the 500 ohm resistor with this orientation. And you can see that that would be the voltage across the resistor would be V3 minus V2, and I divide by 500 ohms, plus IB, that's going to be V3 over 500 ohms, and this is equal to 4 milliamps. Okay, again, I can collect terms here that, so I can collect all the V2s and V3s, and I'll have minus V2 times 1 over 500 ohms plus V3, which will be 1 over 500 ohms plus 1 over 500 ohms is equal to 3 milliamps. Okay. So it's pretty messy, but I now have 3 equations and 3 unknowns, and all I need to do to be done here is solve these 3 equations and 3 unknowns. And I'll get rid of the parts that we don't still need to keep, try to free up a little bit of space. But before I do this, I'd like to point out you may be intimidated by the fact that you have to go through each of these nodes and come up with these equations. But it turns out there's a pattern here that makes it not very hard to do. So if I go back to node 1 and I look at the equation that I got for node 1, you'll notice that I have V1 and then I have a 1 over 500 ohms plus 1 over 500 ohms. That corresponds to this resistor and this resistor. So basically I take V1 and multiply it by the sum of the reciprocals of the resistances to which it's connected. I have a minus V2 and then 1 over 500 ohms. That comes from this resistor as well. And so you'll notice that V1 is connected through this 500 ohm resistor to, or node 1 is connected through this 500 ohm resistor to node 2. And that 500 ohm resistor shows up as 1 over 500 ohms, and I've got a negative sign on V2. The current that's flowing into the node is 3 milliamps. So once you've had some practice, you can actually look at a circuit and just write down these equations that you need to solve in order to find V1, V2, and V3. Okay, so again, it's not very tidy, but I do have my 3 equations that I need to solve now. And so Well, let's go back to our list of things to do. We've applied KCL to each non-reference node. We found currents in terms of node voltages. We got then a system of equations. So the last thing we need to do is solve this system of equations. Let's see what's an appropriate color for systems of equation solving. We'll use this. So all we have to do now is solve this system of equations. Again, back when I was taking this material as a student, we now had another 15 or 20 minutes worth of work ahead of us. There are many ways that you can solve systems of equations, and if there's enough interest, I'll actually probably just post a video that shows the different ways you can do it. You can use tools like MATLAB, or Octave. You may actually have a calculator that will solve systems of equation, or there are resources online. And today I'm going to use an online resource, not because I think it's necessarily better than anything else, but it's handy. And that online resource is Wolfram Alpha. Again, I'm not endorsing Wolfram Alpha, other than to say it's really pretty handy for stuff like this. So all I need to do then to solve the system of equations is type it into this window in Wolfram Alpha. So let's see. Our first equation is going to be V1 times 1 over 500 plus 1 over 500 minus V2 times 1 over 500 is 3 milliamps. Now, when you're solving this system of equations, you need to be a little careful because most of these numerical solvers don't understand units. So you can put 1 over 500 plus 1 over 500. You don't want to put 1 over 500 ohms or 1 over 500 somethings because the solver will get confused. So we're hoping that you've been paying careful attention to units so you'll get it right. We have 3 milliamps, so that's 3 e to the minus 3 amps. So I've entered in my first equation. This is the equation that I got from node 1. So let's go back to see what we need to put in next. We have our equation that we got from node 2. So it's going to be minus V1, 1 over 500 plus V2, blah, blah, blah. So let's bring that up. So we'll have minus V1, 1 over 500 plus V2, 1 over 500 plus 1 over 1000 plus 1 over 500 minus V3, 1 over 500. Now this guy is equal to 0. Okay, so now we've typed in our second equation, and you'll notice that we separate equations in Wolfram Alpha by commas. So let's look at our last equation. It's this top one in pink. Minus V2 times 1 over 500 plus V3 times all the stuff there is equal to 3 milliamps. Whoops, and I made a mistake there. You'll notice that this current here is 4 milliamps, not 3 milliamps. That could have been tragic. So I don't know what I was thinking there, but it clearly wasn't right. So let's type in our last equation. Let's see if we can actually type in our last equation. Okay, so it's minus V2 times 1 over 500 plus V3 times 1 over 500 plus 1 over 500, and this is equal to 4 milliamps. Okay, so if I've typed this incorrectly, I just hit return and wait for Wolfram Alpha, and it tells me how it's interpreting my input, and then it gives me alternate forms, which really aren't all that helpful. And And then it gives me a solution down here at the very bottom. You can see the solution. And that tells me then that V1 is going to be 4/3 volts, V2 is going to be 7/6 volts, and V3 is going to be 19/12 volts. One of the interesting things about Wolfram Alpha is it gives you exact solutions where it can. If you want to see an approximate form, this gives it to you in decimal values. So this is 1.33 volts, 1.667 volts, and 1.583 volts. Okay, so that was painless compared to the way I had to do it. Your lives are so much better now. So what this tells me then is that this, I can say then that V1, let's see, V1 was in light blue. V1 is 1.333 volts. Again, this is now the voltage at V1 with respect to this reference node. V2, whoops, let's get the right color for this. We don't want to be more confusing than we have to be. V2 is 1.667 volts, and V3 is 1.583 volts. So our original question was, what's the voltage across this 1K ohm resistor? Let's see, what's a good color to highlight the correct answer in? Too many choices. Okay, we'll do it in purple. Okay, so we're trying to find the voltage across this resistor. Well, the voltage across this resistor is V2. So that tells us then that our desired answer is 1.667 volts. Okay, well, hopefully this was useful. Again, the goal of this was to introduce nodal analysis. So we go back and look at the steps. We assigned the reference node. We assigned the node voltages. We applied KCL to each non-reference node. Then we solved the system of equations that we got. And that pretty much was it. Now, of course, I chose the simplest circuit that I could to make this as clear as possible, in the sense that this circuit has only current sources. You'll notice that I have just a current source over here and a current source over here. Doing nodal analysis with just current sources is easier than doing nodal analysis with voltage sources. So in subsequent videos, we'll show you what to do if you have a voltage source. First, we'll start off with independent voltage sources, and then we'll move on to dependent sources. In fact, with dependent sources, things get kind of interesting, but they're still fairly doable. So hopefully this has been helpful. Thanks for watching.